Welcome to my YouTube channel. Today we will discuss about how to design double gate MOSFET, comparison between double gate MOSFET versus SY silicon on insulator, and one more comparison between double gate MOSFET versus bulk MOSFET. In this presentation I will tell you about how to extract different parameters such as subthreshold slope, threshold voltage, on current, off current and their ratio, and the last one is most important, DIBL. DIBL is drain induced barrier lowering. I will tell you about how to find out these parameters with the help of the SilvacoTCAD tool. Let's start. To study the design and characterization of double gate MOSFET using SilvacoTCAD tool. A double gate MOSFET consists of two gates that may be aligned or misaligned. In the double gate MOSFET, the channel is controlled by two gates. In this double gate MOSFET, the channel can be fully depleted or partially depleted. It will all depend upon the thickness of the substrate. In this example, we are considering symmetrical double gate MOSFET. The driving capability of double gate MOSFET is almost double of the single gate MOSFET. Double gate MOSFET has a number of advantages and disadvantages. The main advantages of double gate MOSFET is very low off current. This will increase the ion divide by Ioff ratio. If you talk about the disadvantage, in case of misalignment of gates, this will increase the leakage current in the device, which leads to more power dissipation in the device. And one more thing, in the double gate MOSFET, due to two gates, top gate and bottom gate, parasitic capacitance will increase. This means in double gate MOSFET, the parasitic capacitance is very high in comparison to single gate MOSFET. The specification used in the designing of the MOSFET are: the doping concentration of the source and drain is 10 raised to power 20, doping concentration of the channel is 10 raised to power 18, thickness of the gate oxide 3 nanometer, length of the MOSFET 500 nanometer, length of the channel 100 nanometer, and the width of the MOSFET is 30 nanometer. Let's go to the code. This is the double gate MOSFET code. You can also copy the code and run your Silvaco. This is the meshing. The total length of the device is 250 nanometer. For Y direction, the meshing is this from 0 to 20 nanometer. Next, region with material. Region number 1 is air, region number 2 is SiO2, region number 3 is again SiO2, region number 4 is silicon, region number 5 is again silicon, and 6 is silicon with their positional parameter. I have already told you about how to write code in Silvaco. You can watch my previous presentation for understand how to write code in detail. Next is the electrode name, gate, gate 2. We are using the two gates, source and drain with their positional parameter. This one. Doping information 18, 20 and 20. For channel region is 20, for source and drain region is 20. Interface charges at SiO2 interface is 3E10. Next one is the contact name, gate. We are giving the same work function to both of the gate terminal. And we have applied the command common gate. This means if you are applying the voltage at any of the gate terminal, the same voltage is on another terminal, another gate terminal. Source terminal and drain terminal. These are the models: concentration mobility, SRH, auger, BGN, band gap narrowing, field mobility and print. Next is this one is the code. This one is used. I have already told you about this code to obtain the energy band diagram, electric field, electron density, potential, in structure file. You have to use this code in your double gate MOSFET code. Next is the solve initial, solve previous. One more thing, to find out the DIBL, we have to operate your code for two drain voltages. First, we have operate the code for drain voltage 50 millivolt. B drain 0.01, 0.02, 0.03 up to 50 millivolt. Next, log, solve, Tony plot, solve gate voltage to V0 to 1 volt. Gate voltage is same, but the drain voltage is different in these two VT code. First I run my program for VDS 50 millivolt. Next I have run the same code with the different voltage, VDS voltage. Now the VDS voltage is 1 volt, in which I have find out two threshold voltage, one for the 50 millivolt VDS and another for the 1 volt VDS voltage. When the value of the current is reaches to the 10 to the power minus 7, the corresponding voltage is the threshold voltage. We have find out two VT voltage. Next we have plot these two log file, one for the 50 millivolt and one for the 1 volt in the same graph with the help of this command overlay. Next DIBL. The formula of the DBL is the threshold voltage 1, threshold voltage 2 divided by the drain voltage 1 volt and the another drain voltage 50 millivolt. Next is the subthreshold voltage. Detailed about these parameters in the next slide. Subthreshold voltage, you have to use this command. For Ioff current, you have to use this command. Simply you have to find out the value of the y-axis when the value of x-axis is 0. It is at point 0. For own current, you have to find out the value of the y-axis when the VGS voltage is at 1 volt. Next, for finding the ratio, you have to divide I-on divided by Ioff. Next, for finding the transconductance, you have to use this command. I think you have noted down this code. After run this code, you will get two log files, one for the VDS 50 millivolt and one for the VDS 1 volt. This is the graph file for VDS is equal to 50 millivolt and this is the graph file for VDS is equal to 1 volt. Log file. Y-axis is in log form. The maximum value of the current is approximate 10 raised to the power minus 4 and the off current is approximate is in between the 10 raised to the power minus 10 and 11. But in case of when the VDS is 1 volt, we observe that the off current is low at 50 millivolt. When you are increasing the VDS voltage due to DIBL effect, the off current is increased up to the 10 raised to the power minus 10 to 11 ampere per micrometer. Let's go to the code. When the VDS voltage is equal to 50 millivolt, the threshold voltage is high, is at 0.278 volt. When the VDS voltage is equal to 1 volt, the threshold voltage is reduced to 0.173411 volt. To find out the DIBL, you have to use the formula VT voltage at 50 millivolt minus VT voltage threshold voltage at 1 volt divided by the supply voltage 1 volt minus 50 millivolt. You will get the DIBL. You have to find out the DIBL in millivolt. You have to multiply by 1000. It is approximate 110 millivolt. Subthreshold slope or volt, you will get approximate in millivolt 82.95 millivolt per decade. Ioff current when the VGS voltage is 0 volt is approximate 10 raised to the power minus 10 and the on current is approximate 0.4 milliampere, and after dividing you will get the Ioff ratio is 485664. You will get the GM.dat file. By using this file you can find out the transconductance. This is the final structure file you will get after run the code. Next slide. Comparison of capacitance voltage curve. From the comparison graph shown in the figure, we observe that the capacitance in the double gate MOSFET are more in comparison to the single gate MOSFET. This is because of the fact that in double gate MOSFET, two junctions are formed between the channel and the gate, one for the top gate and another for the lower gate. Due to the high parasitic capacitance in double gate MOSFET, the gate capacitance is very high in comparison to SOI or single gate MOSFET. This will increase the capacitance between the gate and the oxide. This also increases the diffusion capacitance of the device. Next is the comparison of the SOI silicon on insulator MOSFET versus double gate MOSFET. One more thing, the double gate MOSFET has lower resistance at channel in comparison to the SOI MOSFET, because in SI MOSFET substrate is present near the channel, so that the channel resistance is high in case of SOI MOSFET as compared to double gate MOSFET. We can observe that the on current of double gate MOSFET is high as compared to SOI MOSFET. This is the graph showing the comparison in the transfer characteristic curve of the bulk MOSFET versus double gate MOSFET. The presence of double gate provides more electrostatic control over the channel, in which drain field line cannot affect or disturb the channel. One more thing, double gate MOSFET also reduce the short channel effects, so that the leakage current of double gate MOSFET is less as compared to bulk MOSFET. The double gate MOSFET are of smaller dimensions as compared to bulk type. In case of bulk MOSFET, we are using the substrate in the bottom side, but in case of double gate MOSFET, we are using the another gate terminal at the bottom side, so that the leakage current is low in case of double gate MOSFET as compared to bulk MOSFET. Now we will discuss the parameter we can extract from the Silvaco code. These parameters affect the overall device performance, such as subthreshold slope, threshold voltage, on current, off current, I-on/I-off ratio, drain induced barrier lowering. First one is the subthreshold slope. This subthreshold swing of a device is defined as the change in gate voltage which must be applied in order to create a 1 decade increase in the output current. Subthreshold swing is the inverse of subthreshold slope. The formula of the subthreshold slope is this one: ln 10 kt divided by q into 1 plus cd divided by cux. CD is depletion layer capacitance, cux is the gate oxide capacitance, kt by q is the thermal voltage. You know that the value of the kt by q is approximately 26 millivolt. Subthreshold slope is depend upon the depletion layer capacitance CD and gate oxide capacitance COX. CD, depletion layer capacitance, is increased with source dropping. Reducing CD not possible with bulk SI technology. COX increases. If you want to decrease the subthreshold slope, you have to reduce the thickness of gate oxide. COX increases with the decreasing TOX. In case of MOSFET, subthreshold slope is equal to 60 mV into 1 plus CD by COX. Depletion layer capacitance is very high in case of MOSFET as compared to gate oxide capacitance. If you are reducing the gate oxide capacitance is more to increase the subthreshold slope, it will increase the leakage current in the device, so that the subthreshold slope in case of MOSFET cannot reduce from the 60 mV decade. It is always greater than the 60 mV per decade. Next is the threshold voltage. Threshold voltage is defined as the minimum voltage that is required to make the transistor on. Transistor may be either NMOS or PMOS. For NMOS, the value of threshold voltage is positive value, and for PMOS, the value of threshold voltage is negative value. The threshold voltage equals the sum of the flat band voltage twice the bulk potential and the voltage across the oxide due to the depletion layer charges. This one. Flat band voltage is equal to phi m minus phi si minus qf by cux. For short channel MOSFET, VTH threshold voltage depend upon the source doping and the junction depth. Next is the on and off current. I-on current, when the VGS is greater than VTH threshold voltage, N channel MOSFET turns on, current starts flowing in the circuit due to traveling of electrons from source to drain. This current is called on current. Ioff current at VGS is less than VTH threshold voltage, N channel MOSFET is in off state. However, an undesirable leakage current can flow between the drain and the source. This current is called off current. Ioff is the ID measured at VGS 0 volt and VDS is equal to VDD supply voltage. It is important to keep Ioff very small in order to minimize the static power and power dissipation. And the last one is most important, DIBL. First we will discuss about DIBL theoretically. This effect is better understood when we see the potential barrier profile that an electron has to overcome to go from source to drain. Under normal condition, at VDS is equal to 0 and the VGS is equal to 0 volt equilibrium condition, there is a potential barrier that stops the electron from flowing from source to drain. The gate voltage has the function of lowering the barrier down to the point where electrons are able to flow. Ideally, this would be only voltage that would affect the barrier. However, as the channel becomes shorter, a large VD widen of the drain depletion region to a point that reduces the potential barrier. For this reason, this effect is aptly called drain-induced barrier loading. The top figure shows a cut of a short channel and a long channel. Short channel by solid line and the long channel by dashed line. Solid line and dashed line. The bottom part shows that the potential barrier profile along the surface of the channel from source to drain. In the left hand side of the figure, this one is VDS is equal to 0 volt. And in right side of the figure, VDS is increased to show the DIBL effect. From this figure, you can observe that if you are increasing the VDS voltage, the width of the depletion layer is start increasing. This will move the barrier down. Electron can easily move from the source to drain when the VGS voltage is less than threshold voltage. You can show that this is the DIBL. If you are increasing the VDS voltage up to a maximum voltage, this barrier is down, then the electron can easily move from the source to drain. This is accurate DIBL. Now we will discuss DIBL practically. The DIBL effect can be calculated by measuring the threshold voltage as the function of two extreme drain voltage. First we have find out the threshold voltage at 50 mV VDS and another is when the VDS is equal to the supply voltage at 1 volt. We have found that from this figure at 50 mV VDS the threshold voltage is 0.6 volt. When the VDS voltage is increased to the supply voltage at 1 volt, the VDS voltage threshold voltage is reduced to 0.54 volt. This is for the example purpose. By mathematical formula, DIBL is find out by threshold voltage at the lower VDS minus threshold voltage at higher VDS divided by supply voltage higher VDS voltage minus lower VDS voltage. This is the graph for the different example. This is the output for the different code. In this example, you are getting the DIBL is approximate 60 mV per decade. The code I have discussed earlier in which we are getting DIBL is approximate 110 mV. One thing I forget to discuss is slightly drawback of double gate MOSFET structure arises due to the misalignment of gates, but it can be optimized by careful design and simulation. So that's all for today. If you like my video, please like and subscribe my channel and share with those who need it. Thanks for listening. Please stay tuned.